Welcome back to the Deep Dive. Today we're taking a closer look at some pretty cool tech you sent over, specifically Hasco's LittleBend cables, ultra-flexible RF and microwave cable assemblies. We've got quite a bit to unpack here. A LinkedIn post showing off some real-world applications, a technical paper that gets into the nitty-gritty engineering behind it, and even a selection guide with all the detailed specs. I mean, these are more than just cables, right? They're crucial components in some really advanced technology.
Yeah, exactly.
So our mission today is to break down what makes LittleBend so special.
Right, and why it matters for anyone interested in the cutting edge of electronics, which...
which I know you are.
It's kind of our thing.
Yeah, that's why you're here.
Yeah.
Okay, so let's start with the problems that these cables are designed to solve. The technical paper didn't just say, oh, hey, old cables are too stiff. They laid out some serious challenges for engineers. What were some of the big ones that stood out to you?
Well, first off, think about how much smaller and more powerful our electronics are getting. I mean, every year, everything is just shrinking.
Yeah.
So space inside these devices is it's incredibly valuable. Now, traditional RF cables, they're not exactly known for being bendy.
Right.
And that can make them a real pain to work with when you're trying to cram everything in. It's almost like trying to fit a bunch of those stiff straws you get at the coffee shop into a tiny lunchbox.
I can see that. Lots of awkward bends and wasted space.
Exactly.
And you can imagine forcing these inflexible cables into tight corners probably isn't great for the signals they're carrying, especially at high frequencies.
Yeah, that's another major challenge. It's not just a mechanical issue. We're talking about signal integrity here. You know, at high frequencies, the quality of the signal, it's incredibly sensitive to physical stress. Bending a traditional cable the wrong way can actually distort the signal, kind of like kinking a garden hose and reducing the flow of water.
Makes sense. And then there's the whole issue of right-angle connectors.
Yeah.
You know, at first glance, they seem like the obvious solution for tight spots.
Right.
But the paper suggested they actually introduce a whole new set of problems.
They do. Yeah, you're right. They can help with routing in tight spaces, but they also introduce signal loss and create points of mechanical stress on the cable.
Huh.
It's a classic engineering trade-off. You solve one problem, you create two more.
Right, right. And finally, the paper really emphasized durability. I mean, these cables are often operating in some pretty rough environments.
Absolutely. Think about the vibrations in an aircraft or the temperature extremes in an industrial setting.
And yeah.
Or even just the constant movement in a robotic arm. These cables need to be tough.
They need to be able to take it.
Yeah, they need to be able to hold up under pressure and maintain their performance over time. So Hasco with this LittleBend series, they're not just making a bendier cable. They're really rethinking how these interconnects are designed to overcome all these limitations.
So LittleBend is like the superhero of cable assemblies. Ultra flexible, but without sacrificing performance.
Exactly. And that's the key innovation here. That level of flexibility, it means you often don't even need those right-angle connectors anymore.
Ah, I see.
If the cable itself can handle tight bends smoothly and reliably, you eliminate a potential source of signal degradation and mechanical failure. It's all about simplifying the design and boosting the reliability of the entire system.
So let's talk numbers for a minute. The technical paper mentioned some impressive bend radii for LittleBend. Can you break that down for us? What does that actually look like in the real world?
Sure. So think about it this way. For a static bend, you know, where the cable is installed and stays put, LittleBend can handle a curve as tight as 0.2 inches.
Like 2 inches.
That's about the thickness of a few coins stacked on top of each other.
Okay.
And even for a dynamic bend, you know, where the cable's constantly moving, it can still handle a radius of 0.4 inches, about the diameter of a pen.
Wow, that's impressive.
Yeah, and that kind of flexibility, it's a game changer when you're dealing with these tiny devices where every millimeter counts. It gives designers so much more freedom.
Right. Now, another spec that jumped out was the shielding effectiveness.
Yeah.
Greater than 90 dB. Now, I'm sure our listeners are familiar with dB, but can you remind us why that number is so important?
Imagine you're in a crowded room with lots of people talking.
Okay.
That's kind of like an environment with a lot of electromagnetic signals flying around. Now, shielding effectiveness, it's basically how well a good pair of noise-canceling headphones can block out all that background noise.
Gotcha.
So greater than 90 dB means these cables are doing an amazing job at preventing electromagnetic interference from leaking out of the cable or into it.
So it's about keeping those communication lines clear.
Exactly. And in sensitive applications like aerospace or medical equipment, that's absolutely crucial to prevent malfunctions and ensure that the signals are crystal clear.
Right, especially when you consider the potential consequences of a stray signal in those environments. Okay, let's move on to retention force. The paper highlighted that LittleBend has a retention force of over 90 newtons. What does that tell us about how well these cables stay connected?
Think of it as the cable's grip strength. 90 newtons, that's a pretty strong grip. It means the connector can withstand a lot of pulling or stress without coming loose. In environments with a lot of vibration or movement, a strong retention force like that is essential to maintain a reliable connection.
Makes sense. And I noticed that one competitor, MiniBend, had a lower retention force.
Right.
Does that mean LittleBend is more robust?
Yeah, it suggests that LittleBend is designed for more demanding applications, where a secure connection is absolutely critical. Applications where you can't afford any downtime.
Right. And speaking of demanding applications, the paper also mentioned that LittleBend can withstand over 1,000 flex cycles. How does that translate to real-world durability?
Well, that number tells you how many times you can bend the cable back and forth before you start to see any performance degradation. So 1,000 flex cycles, that's a pretty good indication that these cables are built to last, especially in applications where the cables are going to be flexed repeatedly, like in robotic arms or test equipment.
Now let's get into some of the more technical aspects of signal quality. The paper highlighted phase and amplitude stability. Can you break those down for us non-engineers?
Sure. Imagine you're sending a musical note through a cable. Phase stability is like making sure the timing of that note is perfect, that it arrives exactly when it's supposed to, without any delays or speed-ups.
Okay, I'm following.
Amplitude stability, on the other hand, it's like ensuring the volume of the note stays consistent. No unexpected jumps in loudness or drops in volume.
So even when the cable's bending and moving, the signal stays true to the original.
Right. And in high-frequency applications, even the tiniest variations in timing or signal strength can cause problems. So LittleBend cables are designed to maintain incredible stability in both phase and amplitude, even when they're being flexed.
So how do they actually achieve that?
Well, they can maintain phase stability of plus or minus 4 degrees at 40 gigahertz, and amplitude stability of less than plus or minus 0.05 dB at 18 gigahertz under dynamic conditions. That's pretty impressive. It means the signal stays remarkably consistent despite any movement, and that's essential for things like radar or advanced communication networks where accuracy and reliability are paramount.
Okay, so we've talked about flexibility, durability, signal integrity. Now let's talk about the fundamental electrical performance, specifically the frequency range and signal loss.
Sure.
What can LittleBend handle?
So LittleBend cables can operate at frequencies all the way up to 65 gigahertz.
55.
Which puts them right in the sweet spot for technologies like 5G and satellite communications.
Wow.
And the selection guide provides specific numbers for attenuation, which is essentially how much signal strength is lost as the signal travels through the cable.
Okay.
For example, the HLB098 cable has an attenuation of about 4.5 dB per meter at 40 gigahertz.
4.5.
The lower the attenuation, the better, because it means more of that original signal reaches its destination. Kind of like minimizing friction in a pipe to ensure that you get maximum water flow.
It's all about efficiency. Now, I noticed in the LinkedIn post that the HLB055 cable can handle frequencies up to 110 gigahertz.
Right.
And they mentioned a very low VSWR.
Yes.
Can you explain what VSWR is and why a low number is a good thing?
So VSWR stands for voltage standing wave ratio, and it's basically a measure of how well the impedance of the cable matches the impedance of the system it's connected to. Think of it like how well a puzzle piece fits into its spot.
Okay, I like that analogy.
A lower VSWR means a better match, so less of the signal is reflected back and more of it is transmitted efficiently. Now, a VSWR of 1.41 at 110 gigahertz, that's excellent.
That is excellent.
It means there's very little signal reflection at that incredibly high frequency. However, it's important to note that the selection guide points out that the overall maximum frequency of the assembled cable is limited by the connectors at each end.
So even if the cable itself can handle the super high frequencies, the connectors need to be up to the task as well.
Right. It's a system-level consideration. You got to make sure all the pieces work together.
Right. And speaking of connectors, the selection guide showed a wide variety of options available for little bend cables.
Absolutely. Engineers can choose from a range of connector types, including the common ones like SMA and SMP, as well as more specialized high-frequency connectors like 1.0 millimeter.
Okay.
And that flexibility is great because it allows them to tailor the cable assembly to their specific needs, whether it's a rugged military radar system that needs durable SMA connectors or a sensitive test instrument that requires the high performance of SMP or 1.0 millimeter connectors.
So it's not just an off-the-shelf solution. They can really customize it.
Yeah, exactly. And the example configuration they provided, the HLB098 S1 SMPJ12, it shows how you can specify the cable type, the connectors at each end, and the length to create a custom solution.
Now, the technical paper also included a comparison table pitting LittleBend against some of its competitors.
Yes.
What were the key takeaways from that comparison?
Well, they looked at several key performance metrics and compared LittleBend to offerings from Times Microwave Huber plus Sunner and Megaphase. And across the board, whether it was minimum bend radius, shielding effectiveness, retention force phase, and amplitude stability, maximum operating frequency, or durability in terms of flex life, LittleBend either matched or exceeded the competition.
So they're not just making claims, the data backs it up.
Right. And the paper's conclusion was that LittleBend offers a very strong combination of flexibility, durability, and electrical performance.
That's impressive. So let's shift gears a bit and talk about where all this amazing technology is actually being used. The paper in the LinkedIn post gave some really interesting real-world examples.
Yeah, these applications really highlight why those specific features of LittleBend are so important. For example, in aerospace and defense and systems like radar, electronic warfare, and satellite communications, you need cables that can withstand harsh conditions, vibration movement, and still maintain perfect signal integrity.
Yeah, those are mission-critical systems.
Exactly. And LittleBend's flexibility and shielding capabilities make it perfect for those demanding environments.
And in telecommunications, especially with the rollout of 5G networks, there's a huge demand for high-frequency interconnects that can fit into all that dense equipment.
That's right. 5G base stations and all that millimeter wave infrastructure, they operate at these higher frequencies. And LittleBend's ability to handle up to 65 gigahertz with minimal signal loss makes it a great choice for connecting sensitive RF modules within those tightly packed systems.
Right. And what about test and measurement equipment? That's another area where precision and reliability are super important.
Absolutely. If you're using a network analyzer or an RF probe, you need to be able to trust your interconnects. And LittleBend's phase and amplitude stability, even when the cables are being moved, that's a big advantage in ensuring the accuracy of your test setups and measurements.
I see. Now, one area that I found particularly interesting was medical imaging and research.
Yeah.
Where would you typically find LittleBend cables in those fields?
Well, in things like MRI scanners and high-frequency ultrasound devices,
Sure.
you often have complex systems with moving parts that require high signal fidelity to produce clear, accurate images.
Right.
So the flexibility and strong shielding of LittleBend are really valuable in those sensitive medical environments. They allow for more complex routing and minimize any interference that could degrade the image quality.
It's all about getting that clear picture.
Exactly.
So let's dive into some of the detailed technical specs just to give our listeners a sense of the kind of information that's available. The selection guide provided a breakdown for the HLB098 cable as a prime example.
Yeah, and it's a pretty comprehensive breakdown. For the HLB098, you see a characteristic impedance of 50 ohms, which is standard in RF and microwave systems. The velocity of propagation is 76%, which tells you how fast the signal travels through the cable relative to the speed of light. There's also the time delay per meter, the capacitance per meter, and even the DC withstanding voltage and operating temperature range. All of that gives you a really good picture of its capabilities.
And it also goes into the construction, the different layers and materials used.
Yes.
Why is that level of detail important?
Well, for engineers designing these high-performance systems, every detail matters. The specific materials used for the center conductor,
Right.
the dielectric insulator, the shielding layers, and the outer jacket, they all affect the cable's overall electrical performance, its flexibility, and its durability. Knowing those details allows engineers to make informed decisions based on the specific needs of their application.
So it's about having all the information to make the right choices.
Exactly.
Now, the guide also provided some specifics for the HLB055 cable.
Right.
And it looks like there's some key differences compared to the HLB098.
There are, yeah. The HLB055, for example, has even better shielding effectiveness over 100 dB.
Wow.
It also has a slightly different velocity of propagation and capacitance. And interestingly, the minimum bend radius for the HLB055 depends on whether it's the armored version or not.
Yeah.
The armored version has a slightly larger minimum bend radius, which shows how different design choices can be made to optimize the cable for different priorities. Like maximum flexibility versus enhanced physical protection.
It's a trade-off.
Exactly.
Finally, the LinkedIn post had a simple but effective diagram showing a typical setup where you might use a LittleBend cable. Can you walk us through that?
Sure. The diagram showed a typical RF signal chain you might see in a test setup or an operational system. You have a signal source, like a signal generator, feeding a signal through various components, like an amplifier and an attenuator. And the LittleBend cable is used to connect all those components to the final element, which could be an antenna or a device under test. It's a simple visual, but it really highlights the flexibility of these cables.
Right. It shows how easily LittleBend can fit into all these different configurations while still maintaining signal integrity.
Exactly.
So to wrap things up, it really seems like LittleBend cables are a significant step forward in RF and microwave interconnect technology.
I think so. They offer this impressive blend of flexibility, durability, and high electrical performance, and they address many of the limitations we see with traditional cable assemblies.
And from all the information we've covered today, it's clear that these cables are engineered for those really demanding applications where signal integrity and efficient use of space are absolutely critical.
Right. The level of engineering and the focus on real-world performance make them essential components in a wide range of advanced electronic systems.
So for our listeners, as you consider the growing complexity and miniaturization of electronics, it really begs the question, how will innovations like these ultra-flexible high-performance cables continue to shape the future of fields like aerospace medicine and communication?
Yeah, it's definitely something to think about.
It is. And if you're interested in learning more about LittleBend cables, or if you have a specific need for ultra-flexible RF solutions, the LinkedIn post includes contact information for HSCO. So thanks for joining us for this deep dive.
Yeah, thanks for having me.
We'll see you next time.